we go. Hey, I can draw on this. Yeah. Lines in a graph are allowed to be curved. They don't have to be straight. Generally, we draw them as straight as possible just so it's easy to see what's going on. I find the more curved lines, the more you have to sort of squint to sort of realize what the story is. So it should be pretty clear for A. The vertex with highest degree, we've got D with 1, 2, 3, 4, 5. C has 1, 2, 3, 4. Is anything got a higher degree than D? No. So we might say degree of D equals 5. For B, we want the subgraph of B, C, D, and E. So B, C, D, and E. And we just sort of connect those up with the connections that exist between them. So I'm more messy than normal because I'm trying not to touch the screen because that's going to make the slide go on. C. Would anyone like to come up and have a go at drawing what they thought worked, or did you guys want a little bit more time with C?
Yeah, you don't necessarily like choose that to do everything.
I don't mind to if you
Alright, these are the questions. Right, these are.
Right? You want to have a go? Oh, you're going to do it on the whiteboard? Yeah. Alright, grab a pen. Sorry, I've been sitting in where my water bottle was condensating. Knees weak, arms are heavy. Yep, that works. So who did it in a similar way to Braden, where you've just kept most things where they are, and if there's an edge that crosses, you just turn it in sort of a loop around it instead? You moved E? What did you do with the top with those two cross lines? Alright. Yeah. So those are basically your two options. You can move a vertex or you can move an edge. Myself, I kind of hate loops or like curved edges, so I try and avoid them. So that 100% correct. You could also do it by moving the edges, and that might look something like this. Moving the vertices, sorry. So C, B, D, F, and E. So I've just moved A inside that little triangle of C, B, and D. And I've just moved E off to... Wait, have I missed a... F should be connected to D. Sorry, I did miss an edge there. Then I've just moved E off to the other side so it's out of the way, similar to what Sarah did. Okay. So either way, there's literally infinite ways you could draw that are still correct. But either of those two ways are acceptable, or any combination therein are acceptable as well. Okay. Oh, sorry. Did anyone need another moment on that?
I'm alright, sir.
All right. Couple of people still going. Okay. So guys, can I get you to have a look at these 4 graphs that I prepared earlier? And can you tell me which graph doesn't fit with the other 3? 3 of those graphs are what we call equivalent or isomorphic, which means they're the same, just redrawn differently. And one of them is just a graph that doesn't fit. B, C, B. What did you say, Casey? C. So we've got a pretty 50-50 mix for B and C.
D.
D?
Definitely Yeah, definitely D.
Sorry?
Have like the same vertex.
Yeah, the same. So basically, I'll give you a hint. A and D are the same graph. Because can you see with D, if you move those 2 vertices there, and instead of going around there, the line went through the middle, it'd be the same as A, just rotated. So A and D are definitely the same graph. So
It's C.
it's C? 100% sure?
Yes.
You guys that said C are correct.
Oh, yeah.
I'll show you why. Can you see if you just picked up that edge there and moved it there, you'd essentially have that same one as D, which we already said is the same as A. So A, B, and D are what we call isomorphic or equivalent graphs. The reason C is different, can you see that there's no vertex with degree 1? Is the main thing that stands out straight away. These ones each have a vertex with degree 1, whereas C does not.
Not bad.
Yeah. This is how you tell I have too much time in the mornings when I animate a red circle. Okay, so I will get you to get down this second thing that's just come up here. Graphs that are the same but look different are called equivalent or isomorphic. Whoops, sorry guys. They're equivalent or isomorphic. I believe the textbook mostly says equivalent. I tend to say isomorphic because it's what I was taught, so it's what I automatically say, but I'm going to try and say equivalent rather than isomorphic just because it's just the graphs that include the same. Graphs that are the same but look different are called equivalent or isomorphic. The reason I want to use both of those words is I don't know what it's going to say on your external. And I don't want to have only said equivalent and then on the exam it's like, here's an isomorphic graph, and you're like, what the hell is that? So it is really important to know both forms of the language. Okay, I'll give you another moment for that. I think we're pretty much done there, guys. Yes. Okay, let's keep going. So, the only reason I bring up isomorphic graphs is to talk about planar graphs. So a planar graph are any graphs where there are no crossed edges. Many graphs with crossed edges, sorry, that should be crossed, not gross, my apologies, are equivalent to planar graphs. So the reason we care about equivalent is just because we actually care about planar graphs, and sometimes you'll see a graph with a crossed edge and you just need to be aware you can rearrange it so that it's no longer crossed. Okay? I will get you to just do the first dot point, planar graphs, and here like underline planar graphs or highlight it or whatever makes it stand out. So just that first dot point, and then once you've done that, I want you to redraw these three graphs so that they are planar, so they have no crossed edges. So I'll give you guys a couple of minutes to have a crack at redrawing those ones. Same rules as before, guys. You can either move an edge or move a vertex, whatever works for you and whatever makes it the least complicated. Either way is correct. Pretty much all of those, you just need to move either one vertex or one edge, and that's going to fix stuff for you. So there's a properly planar. There's actually one of the really famous problems with before I said that was going to be I was going to ask who here has looked at a map. That's pretty dumb. But who here has looked at a globe? I know. I was just testing. If you reckon you had a globe and you had to make it so that every country had a color, but no country had the same color as a country that it shared a border with, how many colors do you reckon it would take to be able to, like, what's the minimum amount of colors you reckon you could do that in? 147? It is much lower than that. 20? Much lower than that. Much lower? 5? You're getting close.
3.
Higher than that, unfortunately. 4. Any map, no matter if it's a globe or like a map of like states or a map of anything, you can always color it so that there's exactly 4, with exactly 4 colors, so that no area is ever touching the same color. And that's any map ever. And that's one of the things that planar graphs use. So obviously it has real life applications aside from making maps. Okay, I think we've mostly got that. What I'm going to do, I'm just going to delete an edge and redo it. Did many people do it that way for this one? For this one, I'm going to delete this stuff and move it. And for this one, I'm going to delete an edge and move it. Ah, yes, you move the D inside. Yep. That is a perfectly fine way to do it. Okay. So, whoops, I've jumped ahead. So that is Leonhard Euler looking fly as hell. Euler is actually a really important guy in maths. There's like him and one or two other guys. Basically, every area of maths they've like contributed to and made some new revolutionary thing. So Euler figured out a couple of things with networks and graphs, and he made a formula about it. So if we had a planar graph like that, can you see that planar graph? And that's the one from the thing before as well. Can you see that that has 6 vertices and 8 edges? So that's all right. But there's one other thing. I have to say that each area. So like in here, we're going to call that an area. That's a second area. That's another area. So far I've got 3 areas, and we call them faces. We also count the area outside of the shape as a face. So that shape then has 4 faces. So we have vertexes is 6, edges is 8, faces is 4 for this shape. So I've just redrawn it over here. Euler's formula is that for any planar graph ever, the number of vertexes plus the number of faces minus the number of edges will always equal 2. Every single time ever. So let's check to make sure Euler's not full of it. For our graph, we have E is 8, V is 6, F is 4. So that's our formula there. V plus F minus E is 2. 6 plus 4 minus 8 is 2. 6 plus 4 is 10, minus 8, 2. Checks out.
Well,
Fascinating stuff, isn't it?
wait, can you have cross lines?
No, planar. This only works for planar graphs. That's really important. So you cannot have crossed lines. I didn't put this in the PowerPoint, but I'm just going to explain something real quick. That formula, has anyone ever seen that before? You might have seen it in year 9. Okay, that formula also applies to 3D shapes. So if I had like a little triangular based pyramid, how many faces does that triangular based pyramid have? How many edges? 1, 2, 3, 4, 5, 6. And how many vertices? 1, 2, 3, 4. So F plus V minus E equals 2. So that's plus another multiplier. Faces is 4. Plus vertices is 4 minus 6 equals 2. 8 minus 6 is 2 equals 2. So that's for a 3D shape. But isn't that weird that a planar graph and a 3D shape have the same rule about them? Wow. The reason it works like that is if you represented that 3D shape as a network, where each vertex is a vertex and each edge is an edge. So that's like my top point there. You see that I have like 3 faces plus the face outside. 1, 2, 3, 4 vertices. 1, 2, 3, 4, 5, 6 edges. The reason this formula works for both is any 3D shape can be represented by a network, which is one of the things Euler found out. And I know to you guys that probably doesn't seem like that interesting, but like I said, it does have like a lot of applications in real life. Yes. A sphere is not what we call a platonic solid. So a platonic solid has to have flat faces. There is a version of the four-color theorem on a torus, which is basically a donut, and they can prove that on a torus, the four-color theorem is still true. I don't know how they do it, but it's something I remember learning about once. Okay, can I get you to get down Euler's formula if you haven't already? So just Euler's formula, you might want to use vertex plus faces minus edges instead of v plus f minus e, if that is preferred for you.
Is that a 4 up top?
Yeah. You don't need to worry about that stuff. That's just me giving you some background, that's all. So like I said, this formula is on your sheet that you'll get given in your exam. Oh, and you guys are going to set plans this week, aren't you?
Yeah.
On Thursday?
Yeah.
After school or during school? You guys all have your results. I gave you your results back before the holidays, didn't I? Yeah, I'm pretty sure I did. Alright. I'm just thinking if I need to give you your marks or not. Alright. The biggest trick with Euler's formula, for me at least, is just remembering that outside is also considered a face. That's the biggest sort of place where I can see people messing up. Everything else is just counting. Does anyone still need Euler's formula up on the screen? Nope. Okay, let's keep going. So let's have a look at this fella here. How many edges does that one have? We've got 1, 2, 3. By the way, what I'm doing right here, I strongly recommend. I'd make a little mark or highlight an edge when you count it, just to make sure that you haven't messed up. 1, 2, 3, 4, 5, 6, 7, 8. Edges is 8. Vertex equals 1, 2, 3, 4, 5, 6. And then faces, we have 1, 2, 3, and then the outside is 4. So faces equals 4. The way I remember Euler's formula, guys, you just always minus edges. Add the other ones, minus edges. So v plus f minus e equals 2. 8 minus 6. Sorry. Oh, I got that messed up. V is 6. Faces is 4. Edges is 8. 6 plus 4 is 10, minus 8 is 2. 2 equals 2. Therefore, yes, that is a planar graph. Checks out. I'm going to give you another one. If I told you there's some graph with 7 vertices and 10 edges, would you be able to tell me how many faces there has to be? How could we do that? You could try and draw it. That would be really difficult though. Especially seeing as 7 vertices, 10 edges. That could be drawn a number of different ways. But if I tell you it's a planar graph, is there anything we could do to figure out how many faces it's going to have? Yeah, we just put in the formula. So v plus f minus e equals 2. So 7 plus f minus 10 equals 2. Just plus 10 to both sides. happened there. 7 plus f equals 12, minus 7 from both sides, f equals 5. So for that graph to be planar, it would have to have 5 faces. That's it. Are there any questions on equivalent graphs, planar graphs, Eulers formula? They're pretty they are what they are. How are we going for time? We've got so much time, that's excellent. Okay, oh, whoops, I forgot I had that up there. Can I get you to have a go, question 1 to 4 on page 408 and 409 of your textbook? I expect you guys will finish that reasonably quick. If you would then like to use that time to start working on your homework sheet, you may. And I will stop my recording.